So like I said, forces, motion under forces. That's what I want to do. And I already showed you that was remember the first day, the motion of the Earth around the sun and the moon around the Earth. So that's what they are forces, not too many, and the objects are moving following the laws of Newton. Okay, so that was his discovery, that that's what the gravitation between the gravitational attraction between the celestial bodies is what makes them move, which is a bit surprising if you think about it, because they are pulling together, and yet they are not pulling on each other. So that's a bit surprising. Well, maybe it was at the time. So how do you explain it? Why doesn't the Earth fall on the sun?
Is it because they're moving so fast?
Yes, yes. But they not only fast, it's moving in the different directions. So it's moving off the direction, and that's why it is falling on the sun. It just keeps missing.
Because the sun's moving too.
No, that doesn't matter. You can assume that the sun is location is fixed. It's like this. If you throw an object and it lands, right? But suppose you have a cliff, and then you throw harder, then you miss. Okay, and then, well, maybe it ends, and then, where does it end? Will it come back? Maybe, maybe not. But it will be pretty much, that's how you throw so hard that you miss the Earth. Well, or if you're on the sun, you miss the sun, respectively. So that's roughly an explanation. So you start with something that looks like a parabola. We know that it's supposed to be, but then there's a cliff in the Earth ends. Okay, so is it possible? Obviously. So motion under forces. And this one applies entirely based on laws of Newton, and whether it's gravity or not, it will work with any force. So, for example, oscillation of a spring would follow the same physics. It doesn't matter what the force is. So, for gravitation, it's a gravitational force. For the spring, it is the springing force, whatever it's called. And then if it could be magnet, it could be electromagnetic fields, whatever, or you can maybe flowing through stream or something like that. So anyway, so how does it work out numerically as well as mathematically? But for the most part, numerically, so that we can handle any force. So the main thing is, of course, laws of Newton. F is equal to ma. Which is, however, is only applicable, only workable if only if when the acceleration is fixed, but which it does, force is fixed, but it might be not. So this may be variable. If it is variable, then the acceleration is variable. Okay, but for the most part, what we are concerned, we know that a prime of t is equal to a of t is equal to v prime of t. The velocity is equal to a of t, and p prime of t is equal to v of t. So in other words, it is the second derivative. The acceleration is the second derivative of the location. Location, velocity. Okay, so but these are functions of time. So that is not what you expect. That's not the same. Function of time meaning that time is the variable, the independent variable, and it is. But the problem is that's not what we observe here. The force is variable, but it's variable depending on location. Typically, you certainly can imagine a situation when the force is changing with time. If we have control, for example, driving, you push the pedal, and there is a more gas, thrown into the engine, and you have more power, and you accelerate, right? So it depends depending on time. But if you talk about physics, then there is the setup of the maybe other planets, and they have forces, and then the forces are different in different locations, but they don't change with time. Okay, so that is the challenge. So that is a bit of a mismatch of location versus time as the variable. So so that is difficult, and that is sets up a differential equation. For example, what I just talked about. Say as an example, so gravity is gravity is constant, but gravity along close to the Earth is constant, but because we're moving away from the center of the Earth so little that we do not feel the difference of how the gravitation decreases. We're moving away from the center of the Earth, the gravitation decreases, but we just don't feel the difference because it's so small, the motion is so negligible. So constant. But for a given distance from the center of the Earth. You already see that the given distance from the center of the Earth, it is about location again. Okay, so roughly this is what it looks like. So this is, say, the Earth. Okay, and on the center on the surface of there is one gravitational force, and then as you move away along each of these circles, the gravitational force is the same. Okay, so once again, if you stay on the orbit, ideal circular orbit, then the force will remain the same. Let me illustrate it with this way. So it will be the same, but it will be directed towards the center of the Earth. Backwards, right, like this. Okay, so the closer you are, the bigger the gravitation. So you see the pictures. So I'm trying to make the inside arrows longer in comparison to these, even though the direction is the same, but the magnitude of the attraction is smaller. Okay, so that's how roughly law of gravitation works, and it could be, and there you remember the laws of gravitation. It is the magnitude is proportional to the inverse of the square of the distance. Remember that? Laws of gravity, of Newton's law of gravity. So that doesn't matter the way what the force is exactly, doesn't matter. That did matter for Newton because he did it by hand in a way usual for that time. But this is only meant to indicate that this is a picture that remains the same in time. It does not vary. So this is what's important is then we concentrate on the acceleration, which is, so acceleration can be found for each location. So whether that m gets involved or not, it really doesn't matter. That's just a coefficient. So, and we assume that the object that's moving has the same mass, and so the difference between acceleration and force is really not something that we worry about. Like I said, it's just a coefficient. We can assume that mass is equal to 1, and then we're done. So which means that if we know the force, we know the acceleration, and then we proceed this. Suppose we know the force, then we can find the velocity. How do we find velocity? Calculus-wise, if we know the acceleration.
You find the
Integral, right? And then the same thing is done with the, then find the location. Also an integral. Well, hold on, let me, I think I actually deviate from the idea that I tried to explain. The problem is we cannot integrate. because the velocity is so we know the acceleration, but it is found for each location. It's not a function of time, so there is nothing to integrate. So roughly speaking, this is what could be, say, this equation is correct, but the equation that at the top, v prime is equal to at, and suppose we know a, but it is not a function of time, because as you move for the next location, the force and the acceleration also changes, right? So this is this might be my trip, hypothetically, and as you can see, as I move through this path, I will have different. The effect of the force will be varying. So I'm getting closer to the Earth, so the force will increase. Okay, so and it will depend on the location, not on time. So roughly, this is what we might. Well, I mean, we know that p double prime is equal to a, except this is what it looks like. P double prime is equal to, say, f of p. Okay, that's a differential equation. Okay, so the function, like I said, this is location, and our acceleration depends on the location. So that's a complicated equation because we cannot solve it by integration. Because it seems like we need to integrate f, but unfortunately f is not a function of time, it is a function of p, location. And this is acceleration. So I don't want to go into how Newton did it and people since him, but let's just go into numerical idea. And numerical, the way we did it, and that's how those simulations are produced. It is we are assuming that the everything is changing incrementally. So changing is incremental. So meaning that the location changes abruptly, jumps, okay, and velocity changes also abruptly, which means that we could solve this problem with no difficulty. Because also the acceleration also changes abruptly. Location changes abruptly, then the acceleration also changes abruptly. Okay, so that's how does it work? So we're going to need initial location and initial velocity. Okay, so given initial location, say p naught, and initial velocity, v naught. Okay, so in other words, we might be here somewhere. Okay, and we know that's location, but we also know the velocity. So like how fast we're going in what direction. Okay, so and then how does and we know and then we know here it is. This let me circle the three things that we are given, and it should be enough. These are three: the initial location, initial velocity, and the acceleration for every location, which is this function over here. Okay, so for every location. For our path, we don't know what path is, but we know that if we know where we're located and which way we're moving, we're going to know the acceleration. Okay, so based on that acceleration, and then the plan works out. Based on the acceleration, we find the velocity. Based on the velocity, we find our next location. Not all locations at once, as it was so nicely done when you just integrate whenever it's possible, but this one is not. So, by the way, the method itself also goes back not long after Newton. It was done by Euler, and so that's how they still do it a lot of it this way. So okay, so initial location p naught. The next one is the part of the simulation is delta t, time increment. Time increment is will be the quality of our approximation. Okay, so we know we decide that everything changes incrementally, but how often? How often do we check out our speedometer? Remember that we check speedometer is different periods of time to find out how fast we're going to estimate our location. This is similar, except well, slightly more complicated. So let's see. So we know the initial location and initial velocity. Then, then what? Based on these two, what can I find? Just these two, what can I find? Approximately. The next location. If you know the initial location, initial velocity, then you can find the next location. P1. Okay, so how do we find P1 from this data?
Would you turn into a line with mx plus b with the velocity being the m and then the p0 being the b?
That's right. So P naught is b. Okay, the slope is initial velocity and times delta t. That's it. Okay, so that will be your location. When delta t is small enough, you will get pretty good approximation. Okay, so you have your next location. So okay, so that's the starting point. Now the problem is that's not enough. In the setting that we're discussing, this is not enough. Because now how do we find the next location? Next location from this. So next location, P2 is equal to, according to the same formula what I'm going to be writing.
Is it P1
P1.
plus V1?
Really? So the velocity hasn't changed? If the velocity doesn't change, we're going to moving in a straight line.
Doesn't it begin? Or does V naught?
If I put V naught, I will be moving along a straight line. Velocity is the direction. If it's not changing, I will be moving in that direction, incrementally moving in that direction. So it's not V naught, but rather what? Well, there's no trick there. We don't know what it is, but I'll call it V1. It is the next velocity. The next velocity, it's kind of velocity during this period of time, what has happened to the velocity. And we know what has happened to the velocity. From where? From over here. We know the acceleration. Okay, so that is in fact the initial, if you like, we can call it the initial acceleration was some a naught, was known. Okay, the initial acceleration. So I have to actually have an extra information here, inserted maybe here. V1 is equal to, let's express V1 in terms of V naught. The idea is the same. The idea, the relation, remember the relation between position and velocity is the same as between velocity and acceleration. They are derivatives, pairs of functional derivative. So those formulas I want to recycle. So V1 is equal to, look at that line, the first line there. P1 is equal to P naught plus V naught delta T. So what about V1?
So it would be V naught plus A naught delta T?
That's right. Okay, so the velocity has changed. Why? Because the acceleration made it. Okay, so and that creates a cycle of computations. So we every cycle of the computation we're computing the velocity first, and then based on the acceleration, and then the next, and then we compute the next location. So let me mark that this is the cycle that is to be repeated. So first the velocity, the next velocity first computed. Based on that velocity and the previous location, we get the new location, and then everything is repeated. The only tricky part is also to watch out for is that this is going to change too. as we're moving from one location to the next, our acceleration also changes. Okay, so but that is a given. Remember that acceleration is given to us for every single location. So if we know location, we know acceleration too. Okay, so it could be the force might be produced by, like I said, by the gravity or by a spring or anything else. It doesn't matter. It works out in the exact same manner. So you repeat this limit as many times as necessary, and you have the whole thing. There is really no trick, and as you can see, it can be carried out with a spreadsheet. So there is this yellow one is a line that is being repeated. Let me write it out again. So this is how it is. So an is, or rather maybe an minus 1 is known, okay? And then based on an, what we in the next line we are computing d n equal vn minus 1 plus an minus 1 delta t. That's the next one. And then we're also computing pn equal to pn minus 1 plus vn minus 1 delta t. So that little algebra, that one line of algebra with nothing but multiplication and addition will give you a simulation of any kind of any imaginable situation. As long as then once you have this becomes the challenge. Really becomes this: to figure out the forces. You got to set it up. So you have to understand what is going on, which forces, how to add them together, find the specific formula for finding the acceleration or the force for every single location. Once you're done, that formula is repeated in every row. Okay, so let me, if I can find quickly that spreadsheet that does this. And I just have too many of those, so give me a moment. Okay, so well, here's solar system. Okay, so this time this one is slightly more complicated than is meant to be, because I only create two rows and recomputing them like this, and then cycling within the same. So it's a bit. Well, let's take a look at it anyway. Okay, so you can see that all of the ingredients that I have discussed are here. So how we transition from initial situation, which gives you 3 coordinates, that I forgot to mention that these computations are to be repeated for each of the 3 dimensions, or 2 dimensions, depending on how far you're prepared to go. So as you can see, position. Look at that column over here. Should I make it bigger slightly? Okay. So position, 3 coordinates. Okay. Then that's the position of the sun. So forget about it. We assume the position of the sun is fixed. So this is the Earth. This is what we just talked about. As you can see, acceleration, velocity, and position in that order. Okay. So let me see. This is the maybe not this one. Okay. It looks a little bit complicated, this formula, if you're looking at the very top, but it is computing the acceleration based on the location. Look at the references. You see the references over there, the highlighted parts on the right, the purple and the green one, right? So I'm computing acceleration, which is on left, the x double prime on left, that's squared, and it refers to 2 places on right. One is the position and the other one is the distance, which is pretty much just it is entirely, because the distance is computed based on the position, it's pretty much nothing but reference to the position and nothing else. The distance has to include x, y, and z. So that's the complication. But otherwise, that's the reference. And then so that's how we find acceleration. Okay, so that's the first step right there on left. Now what happens with the velocity? Let's see what velocity. And you've seen this formula. I just wrote it. Look at it. The previous value of velocity plus acceleration, the purple one multiplied by h delta t. Okay. So there you go. That it is as that simple. Okay. Similarly, if I do to the position, once again, it will be as simple a formula. It refers to the velocity and the delta t, which is I call h here. Okay. So the previous position plus the velocity, the purple one multiplied by delta t. Okay, so it works out, all works out the same. So these two are very trivial. They're those simple formula that you see. And like I said, the actual physics, the whole physics is located here in this square. Okay, so once again, reference defining acceleration depending on the position, period. And then you compute and compute and compute, and you have the motion repeating itself. I don't want to run the simulation, but you might. Do you remember what it looked like? The simulation of back in August.
Was it
Yeah.
the simulation of the eclipse?
It was a simulation of the eclipse, but it's more complicated because then over see I have to do the same thing for the moon. So I don't want to go that far. So just motion of the Earth around the sun, which is assumed to be fixed. You can do the same with the sun, and then will be that is the simulation that I show you. Remember it's called the two-body problem. Two planets of comparable size, and how they move around each other. So, but with nothing but the gravitation between them. It worked out in the exact same way. Do you remember that one? I think I showed it to you. What I want to a point that I'm making is that you should see it here is that indeed nothing but the physics is the physics over here it is omitted, and only the computation of velocity and position is showed. The physics is actually here, so you have to know exactly what the force is. And then, for example, if you were to do the solar system properly, then you would the force that affected by the moon will be made of two, one from the Earth and the other one from the sun. If the sun is sufficiently contributes, not a lot, but it is noticeable apparently how much it contributes to the motion of the moon. If you are not in the this is physics, okay, goes back to Newton. So that if you are able to reproduce Newton's results, even though in a numerical way with help of a computer, then yeah, you could feel kind of good. But on the other hand, then you could modify this and introduce any physics that you want. So including the functions that are totally incomprehensible. They cannot be integrated with any tools that we have or could possibly have, because they could be entirely, I could randomly throw numbers into this universe, and the forces that affect, say, the Earth are entirely variable and they come from nowhere with no physics whatsoever. And it can be done. More practical, I suppose, is replace the rotation of the gravitation that comes from the sun with say spring. I might have a few pictures of that. Yeah, I think that must be it. Why is it not opening? It's still thinking. So motion of this oscillator with one of those. So I imagine that motion of one object on a spring, or maybe a bunch of springs, and you imagine how it's going to be moving. So same story, same method, same spreadsheet, same simulation, but I don't know what it's thinking. I guess it's too big. Let me close this one. It's opening.
I saw this thing about how they're going to travel to Mars and how they're going to
Yeah.
simulate gravity.
Yeah.
Like they were going to attach a tether cable with a big weight, and use the centrifugal, is that the?
Okay.
Centrifugal force or whatever?
Centripetal.
Centrifugal. Yeah, but they're gonna use that force to simulate gravity in a spaceship, but,
You need a big one.
yeah.
You remember the movie Space Odyssey? The guy is running. Have you never seen it? A guy. So that's exactly what he was. So it was done. It was made in the 1960s, and that is it's like you see the guy is running, and in a big wheel. Okay, so the gravity is changing, but because it is rotating apparently, and he just do it for practice. Okay, so we're almost out of time. This is the oscillation. It's done in the exact same manner. Instead of having some kind of simulation, you can see the results only, and the results are, as you can see, oscillation combined with dampening. Okay, so there is for example, if there is an object that is moving there with a spring, it wants to oscillate, but there is also friction, and so the oscillation diminishes. That's what you see, and you have a bunch of the solutions listed, but they all behave the same way. Oscillation that dissipates. Okay, so that's another thing you can do. It's just done exactly the same way, as you can see: position, velocity, acceleration. Okay, so all right, so this might help you with some of your project, but not maybe with yours. But it just happens that you picked I picked projects for you that are not really as much about physics as about some slightly different things. Okay, so see you tomorrow then.